Good afternoon to you all. Today we are looking at Euclidean geometry, grade 12, and for this first lesson we'll be looking at the revision of grade 11 material required for the grade 12 Euclidean geometry. The first point I'd like to make is all about reasoning. You are having an argument with someone with whom you are separated by time and space. It's the barker, effectively, of your argument. And for this point, you cannot use body language or excuses such as, I meant to say this or I intended to say that. Everything that you want to use for your argument must be contained on the answer sheet of your booklet. To this end, your reasoning has to be precise, and in many provinces they are very strict about how you lay out your reasoning. The government has laid out a document, the grade 12 exam guidelines, the address is given here at the top of the screen, and in that document, there on pages 9 to 11, they lay out exactly what reasons they would like you to use for your exam geometry. So what I've got here on the screen right now is a small section of that document, the reasons that you require for the grade 12 material, the midpoint theorem and the proportion theorems. Please look at how these are laid out and look at what supporting arguments are needed or required, because as I said, in some provinces they are stricter than in others as to what you need to write down to support your argument. Please, again, I want to reiterate this. A geometry or Euclidean geometry argument is an argument with somebody who is separated from you with time and space. If I asked you to go to the shops and I said to you, just because, you wouldn't want to do it. But if I said to you, please go to the shops because we are short of bread and milk and I'm trying to bake a cake for your birthday, and I gave you sufficient reasons, you would agree with it. And perhaps even if you didn't want to, you'd be forced to agree with the argument and then maybe go to the shops. So again, please make sure that you understand that everything you need to support your argument must be provided in your answers. The next factor I'd like to go through is, here is an example. Okay, it comes from a past exam paper. And it says, for example, in the diagram below, DF is a diameter of the circle with circle centered O. Chord EG intersects DF at H such that DF is perpendicular to EG. Chords EF and GF are drawn. Angle EGF is 55 degrees. Please determine the reasons, the sizes of D, O2, E2, and E3. Again, this comes from a past exam paper. And what I'd like to look at here is the process of going through a geometry rider. A geometry rider is just a fancy word for a geometry question in an exam paper. Please note that this diagram is given to you and it has been labeled with, for example, E1, E2, and E3. Sometimes they do this, sometimes they don't. If they don't, please feel free to go into the diagram and put in the minor notations 1, 2, and 3. Okay. The next thing I'd like to do is, you may have noticed that I took the trouble to read through this question, in your case, aloud. I would be doing the exact same thing in an exam, except I would be reading it quietly to myself and making sure that all the information given to me in the question is understandable to me according to the diagram. So when they say to me that DF is a diameter of the circle center O, does that make sense to me? Okay, yes it does, because if there is the circle center O over there, DF is a line that is traveling through the circle center, and so DF does make sense to me that it is a diameter. This is important because there are certain theorems that require that knowledge, such as the angle from a diameter is 90 degrees. Chord EG intersects intersects DF at H. Yes, I can see that. The chord EG intersects this other chord at H. That information makes sense to me. Such that DF is perpendicular to EG. Again, please ensure that you understand the meaning of the symbols used in geometry, such as that symbol over there means, that symbol means perpendicular. Okay, we are then further told that EGF is 55 degrees, and again, I'm just going to take note of that. That EGF is 55 degrees, because in this case, it's the only angle size that I have available right now. Okay, so I've read through the text and transferred that information onto the diagram in such a way that I understand that the diagram is complete and that everything that is in the text is understandable in terms of the diagram and vice versa. Okay, now whereas you might see O2 first, angle O2 first, or in other words you could answer question B before you answer question A, generally speaking, these questions are structured, or we would use the word scaffolded, such that D comes before B. Generally speaking, these questions are scaffolded, such that section A comes before section B, comes before section C, comes before section D. I know that sometimes you see section B first. Yes, if you do get stuck, please answer it and at least get marks for that section. But generally speaking, try and proceed in following the order of the questions. Okay, what I'm going to do now is I'm going to clear the diagram. I'm now happy that the diagram is complete and I understand the questions that I'm required to answer. So I'm now going to clear the diagram and try to answer these questions. Okay, so I've been given 3 key pieces of information, and those 3 key pieces of information are that we have the diameter, we have 2 chords that intersect at right angles, and that angle G is 55 degrees. So let's go and look where angle D is. For me, angle D is sitting over here. There is G, and there is D. Now, as I said to you earlier, many provinces allow you to number things E1, E2, E3, for example, but I'd also encourage you to take note of the fact that, for example, angle E1 over here, E1 using that notation is the equivalent of angle D, E, G. Now the reason I would like to emphasize that is it does not only tell you that the angle is at point E, at vertex E, but it also tells you that this angle is being subtended by chord DG. Even though that chord is not currently present, this arc, or this chord, this arc DG, or this chord DG, even if this is not present, is the chord that is subtending the angle E1. So DEG tells me that the angle E, that the particular angle at E, is being subtended by the chord DG. Now that is important and can be very, very useful because, again, we have several theorems that are based on the chords that subtend a particular angle. So when I come back here and I go and say, cool, when I come along and say that I want to look at the angle at G, they did specify earlier that this angle here was EGF. So what have we just discovered? We've discovered that we could consider the importance of that notation as telling me that this angle comes off the angle of the chord EF. Well, in the same way, if I was to look at angle D's real name would be EDF, and that tells me again that it's coming off the chord EF. So I can see here that these 2 chords are coming off the same chord, so these 2 angles are coming off the same chord EF. And so what I'd like to do here is go and start my proof. I've done some thinking about it, and now I can proceed with my proof. Angle EDF will equal angle EGF because we've got angles from the same chord, angles from the same chord, and I'm going to, in this case, specify that that chord is EF. As a result, we know that angle D equals 55 degrees. I'd now like to proceed to angle B, angle O2. Now again, we know that angle O2 is occurring at the circle center. And that comes again from our the trouble we took at the start to read carefully through the entire text. So because they've told us that angle O is at the circle center, we can now again apply some of our knowledge, pieces of knowledge. And that knowledge is that an angle at the center is always double the angle at the circumference. Now, again, O2 is coming off chord EF. We spoke again previously about how that was relevant to the argument. And so again, I might actually encourage you to do exactly what I've done here, and that is to mark the chord EF, whether it be temporarily or permanently, for your own benefit. As a result, O2 will equal 110 degrees because the angle at center is twice the angle at the circumference. So we now know that this angle is 55, and we know that this angle is 110. Again, I always encourage my students to write in on the diagram what they've discovered, so that the diagram is part of their thinking. We now want to move on to question C, which is about angle E2. Angle E2 sits up here, and again I'd like to quickly make sure I know where it is, so I'm going to quickly go and highlight it for myself and say cool, and say this is where it is. Angle E2 is over here, so let's go ahead and think about it. Okay, what do I know about angle E2? Well, I know that angle E2 is part of a triangle. It doesn't exactly come for chord, and in this question there are no tangents involved, there are no parallel lines, so the only real thing that I've got involved here is that this angle is part of a triangle, and so with my limited information I'm going to use the idea that that triangle EOH. What do I know about it? Well, I know that O2 is 110, and I know that the two lines EG and DH are perpendicular to one another. Maybe I can use those two facts to get this to find the size of the third angle of the triangle. And so I'm going to proceed along those lines. As a result, I know that O1 equals 70 degrees, straight line. I know that H2 equals 90 degrees because they told us that DF was perpendicular to EG, and therefore I know that E2 will equal 20 degrees, angle sum of triangle EOH. Okay, finally we want to proceed on to question D. Finding the size of E3. Well, again, E3 is almost like a bonus here. They've given us something that's fairly straightforward. This question occurs so often that actually you should get used to it and realize that it's almost a pattern sum, almost a meme in the way that it happens so often. And what we have here is we have an angle that is part of an isosceles triangle. Now, hopefully you recognize this before I did and saw that because we were given the circle center, one of the things that we should have taken note of is that OE, OF, and if necessary, OD were all radii of the triangle. Now, if they are radii of the triangle, they are all equal in length, which means that we have a situation here where this triangle EOF is an isosceles triangle. Therefore, we know that E3 is equal to 180 degrees minus the 110 degrees divided by 2, because it's the base angle of an isosceles triangle, which gives us 35 degrees, base angle of isosceles triangle EOF, radii OE equals OF. And so what I've done here is I've tried to lay out my work in such a way that all my statements are on the left and all my reasons are on the right hand side, separated from them by a half a page, or some people draw a vertical line to separate their statements from their reasons. I tend to just leave a space between them, and I've tried to keep my work neat. I know my handwriting here has been a little bit untidy, but I have tried to keep my layout at least neat, so that all my statements are beneath one another and all my reasons are beneath one another. This helps the flow of your argument. Please notice that I've given all sufficient information required to support my argument. So I didn't just say angles from the same chord and left the teacher hanging as to I guessed the chord. I've actually labeled that the chord here was the chord EF. Okay, so what I've tried to show you here is that I've taken the trouble to structure my argument giving all sufficient reasons, and that every reason has sufficient information to back up that reason. So my argument flows, and if you accept the first part of my argument, you have to equally accept the final statement in my argument. And that is exactly what happens for a Euclidean geometry rider. You need to have a flow, you need to have a strength of argument, or what is often called the rigor of the argument, such that once you start the conversation, it follows through, that you can't deny the conclusion at the end of the argument. Okay. What I'd now like to do is look at a second example, and the second example is perhaps a little bit more advanced and perhaps a little bit more linked to the matric work. Again, this time I've been given a diagram and a piece of text that describes the diagram. MN is the diameter of the circle O. Again, we have a diameter. MN is reduced to R, such that MN is twice the length of NR. RS is a tangent to the circle, and ER is perpendicular to MR. That is a perpendicular symbol, unfortunately. MS is reduced and meets RE at E. Okay, again, I've taken the trouble to read the text. I know that I've got the circle center. I know that I have a diameter, which means that this angle will be 90 degrees. Whether that is useful or not useful will still be seen. And I do have a line that again is a tangent. And for me, tangents are important because they are a key concept. So if I know that RS is a tangent, I'm going to just quickly mark it here with the highlighter so that I know that that line is a tangent to the circle. Okay, we know that MN equals 2NR. Well, hold on, let's think about that. If MN is twice the length of NR, that means that these three lines are actually all equal in length, because MN is made up of two components, MO and ON, which are radii, and we now know that that piece is equal to those other pieces. Unfortunately, that does not give us an isosceles triangle, but it is something that is important to note. Okay, we want to prove that this SNRE is a cyclic quadrilateral. Again, I would encourage you to take colors and pens. So again, I'm a big advocate of using colors, and we want to try to prove that this shape here is a cyclic quadrilateral. Please note that at this point in time, there's no circle currently drawn around that quadrilateral. The point is we could draw a circle around that quadrilateral if we can prove that it is cyclic. Now, cyclic quadrilaterals are based on two ideas, either that the opposite angles are supplementary or that angles from the same chord are equal. Unfortunately, in this case, we can't prove the angles from the same chord are equal because we don't have that typical shape of a pair of lines crossing. Again, those of you who've spent any time doing your geometry will know that the picture for angles from the same chord is almost always this sort of shape where you have that sort of butterfly almost. In fact, many people call it the butterfly theorem, such that those angles are equal, or alternatively, those angles are equal. That little sub-diagram is not present in this picture, so we can't use it. What I'm therefore instead forced to use is the first fact I mentioned, that in a cyclic quad, the angles are opposite pairs of angles are supplementary. Now again, what I haven't done is marked what I said to you at the start, is ER is perpendicular to MR. We never marked that angle there was right angle. And as soon as we put that in, it now actually becomes quite clear what we need to do, because you can see that this right angle and this right angle are going to play with one another to create the 180 degrees required for this theorem. So we now have a situation where, for question A, we have that NSE equals 90 because of the straight line, and angles from a diameter, and therefore we have that NSE plus ERN equals 180 degrees. Therefore, we have that SNRE is a cyclic quad. Oh gosh, I will get better at this, because the opposite angles are supplementary. Okay, B, how do we prove that RS equals RE? Well, let's think this one through. Okay, RS equals RE. Well, if RS equals RE, that implies that this RS equals RE, there we've marked them. If those two things are equal, it implies that these two base angles would need to be equal to one another. And I think that is how I'm going to proceed in this question. If I make this angle equal to x, then this angle at the top here will be equal to x tan chord, which means that I now know the size of this angle by 3 angles of a triangle, and I'll know the size of this angle by 3 angles of a triangle. Ooh, I've gone bad there. Continuing on with our first lecture on what we need, the pre-knowledge we need to know for grade 12 Euclidean geometry, is the grade 9 knowledge of similar triangles. And if I had two triangles, A, B, C, and some other triangle, D, E, F, such that I knew that this angle was equal to this angle, that this angle here was equal to that angle over there, I would know that triangle ABC would be similar to triangle, well, hold on, we can see that A over here, which was listed first, is paired with angle E. They are the same size. That angle C is in red, is the same size as angle D. Well, if angle C is listed third, I must list angle D as third. And therefore, if angle B is the missing angle, it must be paired with angle F. And some of you guys will be shouting at the screen saying, well, hold on, we know that because 3 angles of a triangle equal 180 degrees, we actually know that this angle must actually also equal that angle. So what we can see here is that the A angle is mentioned first for the angle E. The B angle is mentioned second, and that is actually the same size as angle F. And if you look at it closely, you'll see that angle C is paired with angle D. They are told us as being the same. This is very, very important, because the order in which you list these things is crucial. Because something else happens when I do it in this order. What I get is that angle side length AB will be in proportion to EF in the same way that angle AC, side length AC, is in proportion to ED, and that BC is in proportion to FD, because the triangles are similar. Now, this knowledge of writing down the similar triangles in the correct order, and then be able to write down the proportion statement, is a key skill that hopefully you developed in grade 9. Okay, We also need to quickly discuss similar polygons, because this is not totally the truth when it comes to shapes that are higher than triangles. For example, we have a situation where I can have a rectangle and a parallelogram such that if this was 5 and 5 and 8 and 8, I could have this one being 50, 50, 80 and 80. In this case, the sides are in proportion. That is true. But because the angles are not equal, these polygons are not similar. In the same way, I can have a rectangle and, for example, a square. Now, in these two situations, we have a situation where all the angles are the same. But although these ones have the angles being the same, the sides are not in proportion. As a result, these things are not similar. So what we get, and in triangles and triangles only, is the key idea that there's a tension or linkage between the sides being in proportion and the triangle's angles being equal. And when these two things happen, well, if the one thing happens, it automatically follows that the other thing automatically happens. If the angles are equal, the sides will be in proportion, and the sides are in proportion, the angles will be equal. Now again, what do I mean by proportion? If I gave you a line and I broke it up into a distance of 2 and 5, I know that the one piece is of length, well, is in the proportion 2, and the other piece is in the proportion 5. That doesn't mean to say that they are 2 centimeters long and 5 centimeters long. If I knew that this entire thing was 70 centimeters long, I'd be able to calculate that this portion is 2 pieces of the entire length, and the other piece is 5 pieces of the entire length. Well, again, please understand that that means that I have a situation where the left-hand piece is 2/7 of the 70 centimeters, and the right-hand piece is 5/7 of the 70 centimeters. Now, a key concept here is, where did that 7 come from? That 7 came from realizing that if I have parts to part, I also have the notion of parts to whole. So if the parts to part is 2:5, then I also realize that the parts to whole on the left will be 2:7 or 5:7. Now, something which interests me is that a ratio is almost the same thing as a fraction. And so very often when we write things in proportion, you'll see that we have things written as fractions. And quite simply, something's going on here with the battery here. Quite simply, a proportion means two things are written as the same fraction. So 2/7 is written as 20/70, or could be written, for example, if you had a different situation, as being 14/49. These things are in proportion because the fractions are equal to one another. This is the revision of prior knowledge that you need to know for the grade 12 Euclidean geometry. This ends our first chat. Thank you so much.